So in this video, we're going to talk a little bit more about about isomers. And before I move on, I want to talk briefly about the concept of superimposability. All right. So essentially, the proof that things are isomers versus whether they're not isomers, with the exception of conformational isomers, is whether or not things are superimposable. All right. So if I had these two different molecules, and I've just used these are two tetrahedral carbons with four different groups on them. All right, but you'll notice there's the same groups on each one. All right, and there's a chance that they're exactly the same, but there is a chance that they might be isomers. All right, and the proof would be that they're the same is if you could make them prove that they were superimposable. All right, so what I mean by that is if I were to hold them like this, all right, it's not obvious right off the bat whether they're the same thing or not. But if I take them and I try to put one over top of the other, if these are the same, there should be a way that I can hold these where all of the atoms will line up. All right, and you can see here that if I do it like this, the red of one is right next to the red of the other, green is next to green, blue is next to blue, and white. If I hold it in that same direction without moving anything else around, all of the atoms line up. All right. Okay. So what I've done now is I've taken one of the atoms and I've just switched two of the groups. All right. So again, if you're looking at them like this, it's kind of hard to tell if they're the same or if they're different. Let's try to line things up. All right. So I'm going to line up the white here. So right now I've got the blues lined up. I'm holding those. I've got the whites lined up. But you notice that when I do this, that the greens and the reds do not match up. All right. So what that means is that there's no way I could twist this thing and try to set it on top of the other molecule so that all of the groups would be in the exact same places. All right. The most you're going to get is two of them are in the same place, but two of them are different. All right. So when you're thinking about this concept of isomers, the proof that things would be different is if you tried to twist the bonds around or flip things around and get them so that they're superimposable. If that was totally impossible, all right, then they would be isomers. But if you could get them to be completely superimposable, they would essentially just be the same molecule. Okay, so the next type of isomer I'd like to talk about is what's called a conformational isomer. And this is arguably it's not like the other isomers in that conformational isomers are the exact same compound. All right. The only thing that makes them isomers is that they have a little bit of a difference in the rotation of one of their bond positions. For example, if I have this molecule right here, at this point in time, this would be its exact shape. But if I rotate this bond just a little bit, well, it's still the same molecule, but what you would say is that this is a different conformational isomer than this, all right? And the only thing that's different about those two things is the position in the rotation of that bond, all right? One thing about conformational isomers that is different from other things is that in the other types of isomers that we've talked about, say, for example, this thing versus this thing, you could separate and put this thing into a separate bottle, and you could separate and put this thing into a separate bottle. But with conformational isomers, that's not possible because 1 second later, this bond is going to rotate, and there's no way you can separate these. All right. So one of the most famous examples of conformational isomers has to do with this molecule here, cyclohexane. All right. And there's a lot of molecules that contain substituted versions of cyclohexane. So what I've got here, I've got a little example of cyclohexane here. You can see that corresponds to this structure right here. And I pointed out right here that this is drawn flat. All right. So first thing, notice I haven't put, there would actually be two hydrogens on each of these carbons, but I haven't put those on this model here just for the sake of simplicity. All right. So the thing about cyclohexane is if you saw it like this, you might assume that it's totally flat. All right. The thing about it is if you look at it on its side, all right, you can see that this thing is capable of twisting and bending around a little bit. And the thing about cyclohexane is that it tends to adopt one of two conformations. All right, one of them is what's called this chair conformation. Let me make this a little bit bigger. Okay, so this is cyclohexane. Again, that's flat. But if I turn it like this, you kind of see that this side right here goes up. So this would be like the back of a chair, right? My hand, or actually my pencil right now, that would be sitting on the seat of the chair. And then your legs, picture your legs going down this way. Okay, so this is the seat of the chair. So that's why that's called a chair conformation, all right? And the other conformation that cyclohexane tends to like to be in is what's called a boat. And to turn a chair into a boat, all you got to do is take the footrest part of the chair conformation and you flip it up. All right? So when you have it like this, you can kind of picture as this is one tip of the boat, this is the other tip of the, I guess, like a canoe, and this is the part, the water, it would be floating in the water like that. All right, so the thing about these two conformations is that they're constantly interconverting. All right, it's not like this thing stays permanently like that. The interconversions are happening all the time, and there's no such thing as a bottle of chair cyclohexane versus a bottle of boat cyclohexane. All right, they're the same compound, just in different points of their rotation. All right, so one thing I'm going to point out is that there's actually ways to draw these. All right, when you're drawing a chair, you do kind of like this, and notice that this side right here is deliberately drawn bolder than this one right here. So the side that you're seeing right here would be the side, okay, I've got to get in the chair, would be the side that's closer to you, and these two ones back here would be the ones that are farther away. This would be the footrest carbon down here. All right. So, and also you can do the same type of thing with a boat conformation. All right. Okay. So the next types of isomers I'm going to talk about all have to do with compounds with double bonds. All right. And remember, the thing that's special about double bonds is that you can't have, there is no rotation around the double bond. All right. So this right here, these model kits are actually pretty useful for this because you can see that there would be trigonal planar arrangement around those double bonds. All right. So the first type is what's called cis-trans isomers. All right. And in order for you to have cis-trans isomers, you have to have a double bond where there's one hydrogen and one non-hydrogen on each of the carbons. All right. So to explain that, I've shown this right here. So notice that there are actually two hydrogens that are coming off the double bond, but they're both coming off of this carbon right here. All right. On this side of the double bond, we've got a methyl group and we've got a bromo group. All right. So there's no cis-trans possible here. All right, because you have to have one hydrogen on each of the carbons. All right. So an example of so take a look at these guys right here. All right. So this would be essentially this molecule right here. All right. So the way I'm holding it right here, the green atom right here would be this bromine right here coming down. We've got one of the carbons, this carbon, and then we've got this methyl group up here. All right. And you probably notice that if I take this and I just turn it upside down like that, I would have this compound right here. All right, so these are both the same thing. All right, but the thing to notice about this is that both of the non-hydrogens are on the same side of the double bond. All right, so if you were to take your pencil and just lay it down on top of the double bond, you'd notice that both of these groups are on the same side of the pencil. All right, and that's true no matter how I turn this. And the reason for that is I can't, in order for them to be on opposite sides of the pencil, I'd have to be able to rotate that bond 180 degrees, and I can't do that. All right, so take a look at this molecule right here, and that would be this guy right here. Okay, so holding him in that orientation, all right, it would be like this. And so why are these guys isomers? All right, well, remember the concept of superimposability. All right, well, this right here is This is what you call the trans isomer, and that's when if you take a pencil and you put it along the double bond, you'll notice that the non-hydrogens are on opposite sides of the pencil. All right, so that makes it trans. This guy was your cis because they're on the same side of the pencil. So, but the thing is, if these things are the same, there should be some way that I can line things up so that all the atoms would be superimposable. All right, and if you notice when I do this, this side right here, the white and the black atoms line up perfectly, but on the other side, you'll notice that there's a mismatch. All right. So cis-trans isomers are very common in organic molecules. One thing I want to point out, this trans isomer, one place that you might have heard about that is with fats. All right, fats have these long chains on them called fatty acids, and a lot of those fatty acids have double bonds in them, and around those double bonds they can either be a trans orientation or a cis orientation, and for the ones that have the trans orientation, you call those trans fats, and hopefully you've heard of that before. So for these, you always have to have at least one hydrogen on each of the carbons. All right, but what happens if you have a double bond where you have either 3 or 4 substituents around the double bond? All right, so right here I've shown an example where we have 3 substituents. All right, this would also work if you had a 4th substituent right here, but for this example I'm just showing this with a hydrogen there. All right, so this is going to create a situation where instead of cis-trans, because in order for cis-trans you have to have 2 hydrogens, we're going to have what's called EZ isomers. All right, but the concept is very similar. Okay, so let's compare these 2 molecules right here. All right, well, notice that in this one right here, the bromine and this, I guess you'd call this a hydroxymethyl substituent, those are trans from each other. They're across from each other, where here the bromo and the hydroxymethyl are on the same side of that double bond. All right, so the way that you do this is you look at both of the carbons. All right, and with the groups on that carbon, you're going to prioritize them according to their molar mass. All right, so if you look at the periodic table, bromine is a higher molar mass than is carbon. All right, so this gets the 1 priority, this gets the 2 priority, or you can say the high priority and the low priority. All right, so on this side, we're comparing a carbon, which is what is directly bonded here, to a hydrogen. So the carbon, this would be the high priority group, and this would be the low priority. All right, so again, on each of the carbons, you assign a high and a low priority based on which one's got the higher molar mass. And then what we're going to do is we're going to like put something down the middle of the double bond, like a pencil. All right, and what you want to ask is, are the high priorities on the same side of your pencil? Are the high priorities on the same side, or are they on different sides? We can see here that the high priority, so on this carbon, this is the high priority, and on this carbon, this is the high priority. They're across from each other. All right, so whenever they're across from each other, it gets an E designation. All right, and the E it's a German word. I believe it's pronounced Antigen. I'm having trouble with that. But the key thing to know is when that happens, you put an E there. All right. So the opposite of that. All right. Again, put a pencil along that double bond, and you'll notice that both of the high priority groups would be on the same side. All right. When that happens, it's going to be what's considered a Z configuration. All right. So, and that term actually makes it into the name. All right. This right here would be E 2 bromo 2 butene for all. All right. And this would start with the Z. All right. So the Z comes from the German word zusammen. All right, which means together. But the easy way to remember this is if you were to imagine somebody that had a German accent trying to say the same side. They might say the same side. All right, and when you do that, just remember that's the indication that that's going to be your Z isomer. All right, so just for comparison, what if I were to take, notice this has also got a methyl, hydroxymethyl, and bromo. All right, so would this be a Z or, this would actually be a structural isomer. All right, because you'd actually have to disconnect carbons to make that.